Hello everyone, my name is Choerton, and today I will be presenting my data mining final project. In this study, several classification and clustering techniques were applied to analyze the forest statistics and determine the most suitable predictive model for the dataset. Two datasets obtained from the Ministry of Interior were used in this study. The first dataset contains divorce statistics, while the second dataset contains population statistics. The divorce dataset consists of 618,240 records and 9 variables, whereas the population dataset contains 418,392 records and 7 variables. After data aggregation and merging, the combined dataset was used for subsequent analysis. The target variable in this study is called divorce level, which was derived from the original variable divorce count. 3 categories were defined, namely none, low, and high. Since the target variable represents categories rather than numerical values, it is considered a nominal variable and it's suitable for classification analysis. Next, the independent variables and their data types were identified. A missing value examination was then conducted. The results show that no missing values were observed in any independent variables. Therefore, no imputation or deletion procedures were required, and the dataset could be directly used for model construction. Before constructing the predictive models, several pre-processing procedures were performed to improve data quality and avoid information leakage. 3 major aspects were considered, including variable removal, derived variable creation, and missing value handling. Some variables were excluded because they either contained duplicated information or could lead to information leakage. In particular, divorce count and divorce rate were removed, since the target variable divorce level was created from divorce count. Including these variables as predictors would allow the model to indirectly see the answer, resulting in unrealistically high prediction accuracy. 2 new variables were created during pre-processing. First, population information was added by aggregating the population dataset according to district and gender, and then merging it with the divorce dataset. Second, the target variable divorce level was created from divorce count to transform the problem into a classification task. Rows containing missing values were removed during pre-processing. Afterward, another examination was conducted to ensure that no missing values remained. The output confirmed that the final dataset was complete and suitable for analysis. The original variable divorce count was numerical and highly skewed, with more than 95% of observations having 0 divorces. To transform the problem into a classification problem, the variable was discretized into 3 categories. Observation with 0 divorces were labeled as none, with 1 or 2 was labeled as low, with more than 2 divorces were labeled as high. Finally, one-hot encoding was applied to all categorical predictor variables, including district, marriage type, sex, nationality, education level, and age group. One-hot encoding was selected because it avoids introducing artificial order among categories, preserves the original meaning of the variable, and is suitable for machine learning algorithms, such as decision trees and SVM. In addition, it prevents misleading relationships that might occur when label encoding is used. After completing data pre-processing, I constructed a decision tree model using all variables. The model achieved a testing accuracy of approximately 96.34%, indicating that the decision tree provided good predictive performance for this dataset. Next, an overfitting analysis was performed. All 391 variables were used. The minimum numbers of sample per leaf was fixed at 2, and the minimal split values range from 0.1 to 0.01. As shown in the table, the training accuracy and testing accuracy remained very close throughout the experiment. The results indicate that no obvious overfitting was observed within the tested range, since the difference between training accuracy and testing accuracy was very small. The model generalized well. Therefore, overfitting had not yet begun even when the minimum split value reached 0.01. To reduce dimensionality, two feature selection methods were investigated: chi-square and model selection. After comparing the performances, model selection achieved better overall accuracy and was selected for subsequent analysis. Feature selection successfully reduced the number of variables from 391 to only 20 variables, while maintaining almost identical training and testing accuracies. Therefore, the selected variables produce a simpler and more efficient model without sacrificing predictive performance. The final decision tree model was selected because it achieved high prediction accuracy and showed no obvious overfitting. In addition, feature selection reduced the dimensionality, and a tree depth of 8 provided a good balance between complexity and interpretability. The final tree contained 135 nodes and 68 leaves, making it sufficiently compact and easy to explain. Initially, the decision tree was able to generate decision rules only for the non and high classes. Since no decision rule corresponding to the low class could be found, random oversampling was applied to address the class imbalance problem. After resampling, more balanced class distribution were obtained, allowing decision rules to be generated for all target classes. After resampling, representative decision rules were obtained for the non-low and high classes. Finally, five-fold cross-validation was performed to evaluate the robustness of the model. The average cross-validation accuracy was approximately 19.96%, demonstrating that the proposed decision tree model is reliable and possesses good predictive capability. Here is the five-fold cross-validation mentioned. Next, I applied support vector machine, or SVM, to this dataset. Since SVM is a classification algorithm, the target variable must consist of discrete classes rather than continuous numerical values. Therefore, the original variable divorce count was discretized into 3 categories: non, low, and high. In addition, several categorical variables, including district, marriage type, sex, nationality, education level, and age group, were transformed using one-hot encoding. This method converts categorical values into binary variables and allows SVM to process them correctly. Furthermore, one category from each variable was removed to avoid redundant information. Since SVM is sensitive to variable scales, standardization was applied using standard scalar. Standardization prevents variables with larger magnitudes from dominating the model and improves both the accuracy and stability of support vector machine. The dataset was then divided into 80% training data and 20% testing data. Using this split, the SVM model achieved a testing accuracy of approximately 95.8%, indicating satisfactory predictive performance. To identify the best SVM configuration, two different values of the penalty parameter C were investigated. Both linear SVM and SVC models were compared. As shown in the table, linear SVC and C equal to 0.1 achieve the highest testing accuracy and approximately 96.05%. Therefore, linear SVC with C equal to 0.1 was selected as the final SVM model. Although the training accuracy of all models was similar, this configuration achieved the highest testing accuracy and demonstrated the best generalization performance. In addition, linear SVC is computationally more efficient and therefore more suitable for this large dataset. After evaluating the SVM model, I investigated random forest. Similar to SVM, random forest is also a classification algorithm and requires a categorical target variable. Therefore, the original divorce count variable was discretized into three classes: none, low, and high. One-hot calling was again applied to all categorical variables because random forest requires numerical inputs. This approach converts categories into binary variables and improves computational efficiency by removing redundant information. Unlike SVM, standardization was not required for random forest. This is because random forest is a tree-based algorithm, and its splitting process depends on criteria such as the Gini index or entropy rather than distances between the observations. Therefore, variable scales do not influence the model. After splitting the dataset into training and testing sets, the random forest model achieved a training accuracy close to 100% and a testing accuracy of approximately 96.87%. Although the difference suggests some degree of overfitting, the model still demonstrated excellent predictive performance. Several parameter settings were investigated, including different numbers of trees and maximum depths. Among all configurations, the model containing 100 trees and unlimited depth achieved the higher testing accuracy of 96.87%. Therefore, this configuration was selected as a final random forest model because it provided the best predictive performance. Next, I applied the k-nearest neighbors algorithm. Since KNN is a classification algorithm, the original numerical variable divorce count was transformed into three categories, namely none, low, and high. This allowed the model to classify observation into different divorce levels. Similar to the previous models, one-hot encoding was applied to all categorical variables. Since KNN requires numerical inputs, categorical variables cannot be processed directly. Therefore, categories were converted into binary variables to facilitate model construction. Because KNN is a distance-based algorithm, standardization was necessary. Variables with larger scales could dominate the distance calculation. Therefore, standard scalar was applied to ensure all variables contributed equally and to improve model performance. After splitting the dataset into training and testing sets, the KNN model achieved a training accuracy of approximately 95.48% and a testing accuracy of 94.95%. These results indicate satisfactory predictive performance and good generalization ability. Different values of K were investigated to determine the optimal parameter. Among the values tested, K equal to 9 achieved the highest testing accuracy of approximately 95.25%. Therefore, K equal to 9 was selected as the optimal value. Next, assembled learning was investigated using voting classifiers. Both hard voting and soft voting approaches were constructed based on the best models obtained previously. The results showed that hard voting achieved higher testing accuracy and better generalization performance than soft voting. The performances of decision tree, SVM, KNN, random forest, and voting classifier were compared. Among all classification methods, random forest achieved the higher testing accuracy of 96.87% and therefore demonstrating the best predictive performance. In addition to classification models, K-means clustering was performed to explore hidden structure in the dataset. The elbow method was first applied to determine the appropriate number of clusters. As shown in the figure, the decrease in WCSS became much smaller than K equal to 4, suggesting that 4 clusters would be appropriate. To further investigate the clustering structure, the target variable divorce level was included in the clustering process. 2 clustering solutions were considered, namely K equal to 4 and K equal to 5. Although K equal to 5 produced a lower SSE value, the silhouette coefficient for K equal to 4 was higher, with a value of approximately 0.7. Since a higher silhouette coefficient indicates better cluster quality and separation, K equal to 4 was selected as the final clustering solution. After clustering, the 4 groups mainly differed in terms of population size. Therefore, meaningful labels were assigned to each clusters. These clusters were named low population areas, medium population areas, high population areas, and metropolitan areas. Population size was found to be the most important factor distinguishing the clusters. Majority voting was then used to assign class labels to each cluster. It was found that all clusters was dominated by the non-class. As a result, the classification accuracy obtained by majority voting was approximately 95.27%. This result suggests that the data set is highly imbalanced, and the K-means primarily grouped observation according to population size rather than divorced categories. Finally, all approaches were compared, including decision tree, SVM, KNN, random forest, voting classifier, and K-means. Among all methods investigated, random forest achieved the highest testing accuracy of 96.87%. Compared with a single decision tree, random forest benefited from assembled learning and demonstrated superior predictive performance and robustness. In conclusion, this study successfully applied multiple classification and clustering techniques to analyze divorce statistics. Among all models, random forests with 100 trees and unlimited depth achieved the best predictive performance and was therefore selected as the final model. Thank you for your attention.